Same cost, but better service.
Okay, let us begin. We are delighted to have today Professor Antti Niemi from the University of Oulu. Antti earned his master's and his DSc, which is only in certain countries that they have this DSc, in engineering physics, MSc, and the DSc in mathematics from the Helsinki University of Technology, which I believe today is the Aalto University. And since 2020, he has been a professor at the University of Oulu, where now he's a dean. He's dean of the University of the Faculty of Technology, which includes all of engineering, right, or part of engineering?
Information ICT is in a separate faculty, but all other fields.
Yes, and and this research focuses in developing mathematical models and numerical simulations in structural mechanics, including, of course, finite element methods and analysis of finite element methods, and stress analysis and stability, which we will be speaking about today, more about in the AI era. We're focused on the AI era, so I'm curious to hear what this means. We will see. So anyway, let's give him an applause to welcome.
Thanks for this opportunity. It's my pleasure to be here. I have lost count. It's either fourth or fifth time now here in Chile and Santiago, and with Norbert and Thomas. Principally, we have been collaborating for some time now on different areas. So today I will give like an overview type of talk about certain activities, and I hope not to disappoint you regarding this AI there, but as you see, it's not said as a reference to AI era. So I think we definitely leave that kind of era right now. We're just discussing about co-pilot and language models, etc. But there is actually something related to machine learning also. But overall, it is about, as the title says, to ensure reliability of structural simulations. But let me first start. So I come from Oulu, northern Finland, and since 2 weeks we have now been the culture capital of Europe. And of course, science and culture are also very closely related. Oulu is kind of known as a technological city, perhaps, very much industry and including telecommunications. But now, like I said, it's culture capital, and also various activities take place. So, and then still about this background, so where this talk comes from. So our conditions are relatively north. So these engineering applications, also in Chile, there are many challenging conditions in terms of earthquakes, for instance. Those we don't have, but we have these demanding northern conditions that require, in general, robustness and reliability and awareness of uncertainties in modeling and decision making. And well, this is a marketing slogan, but I kind of like it, the science with Arctic attitude. Okay, that's the background. So the idea is, like I said, so we start from something well known, these principles of simulation governance that are used to ensure this reliability of structural simulations, and then approach this topic through 3 applications, one of which is like AI-assisted structural optimization. Then as second, there is something related to this winter in Finland. So reliability under extreme snow loads and the uncertainties related to those questions. And then last, perhaps more familiar, related to the development of finite elements as to sort of close the loop. So these are the terms that are in the engineering community sometimes quite formally even defined and perhaps even standardized: verification, validation, uncertainty, quantification, and nowadays, I guess, data quality. So this is of course very basic underlying assumption which might sometimes be forgotten, but every time we do any simulation, try to support decision making, of course the underlying assumption is that these results are reliable, credible, and they can be used as a basis for decision making. So this simulation governance as such is like both managerial and technical function. So I think this is very important for the managers leading these construction projects or engineering projects. Well, these core elements were mentioned: verification, validation, and uncertainty quantification, UQ. And the claim is that in this era of AI-driven structural engineering, these are more important than ever. So, like I said, this terminology can vary and it's used in different contexts differently, but the American Association of Society of Mechanical Engineers in their standard defines this so that the verification is concerned with the question that the model is being implemented correctly and there are no errors in numerical solution. And this is, of course, in some sense, a traditional problems for numerical analysis in computational mathematics and mathematics in general, so that we are solving the equations correctly. Of course, one could extend it also to analysis of the model in the first place about existence and uniqueness of solutions. But then the term validation is then refers that the model is a realistic representation of physical reality, and most often this of course involves then comparing simulation results to experimental data, so physical tests and in the field and real world benchmarks. And then the uncertainty quantification could be posed as a question that, well, how confident and are we in the results at the end of the day, and as a result of the various uncertainties in input and model parameters and their propagation to the end results and result of incomplete knowledge or assumptions. So typical examples of activities in these areas, of course, just basic sensitivity analysis. Parameters are being very probabilistic risk assessment that we are shortly prescribing as one of the applications. But then, of course, my civil engineering background concerning large infrastructure, large structures. I mean, for instance, certain constructions, they are unique bridges, specific bridges constructed only once. And there's not like a very mass production or possibility to study in lab all aspects. So it's a one-time experiment. So one really has to be confident then in the simulations and see what testing can be done and analysis and bring these together. So these large-scale projects are very difficult in that respect as compared to certain individual components. So then proceeding, so now to the AIS assisted optimization. So this is a very applied study related to specific code-formed steel structures and their optimization using machine learning. Well, first of all, okay, where the motivation comes from here is again a provocative conceptual picture. Of course, now there is heavy pressure to optimize structures, reduce weight, and things like that arising from sustainability considerations, for instance. So here is some typical situation for a typical structural engineer. So suppose one flight over Atlantic from Europe to New York is taken of order of magnitude of 1,000 kilograms CO2 equivalent. Then by reducing diary, one could say 2,000 kilogram. Stop driving a personal car, maybe 3,000 kilogram. But then if there is a possible to reduce 20% of structural embodied carbon over certain assumption that there's 5,000 square meter on average what the structural engineer is responsible of with a certain amount, so that boils down to 200,000 kilograms. So a professor who teaches 10 structural engineers a year to do that, you can put 0 in the end and then start eating, continue with the well, anyway, this is provocative, but this is the kind of motivation to start to optimize and reduce. So now this
that number there, sorry, number in the bottom there is assuming 20% of structure embodied in where? In every single structure that you're doing?
Yes, like I said, these are averages, and averages is of course complicated, but these are some like rule of thumb numbers that an average structural engineer should roughly responsible a year 5,000 square meters. Of course, the construction industry talks only about square meters, nothing else matters. Square meters. And then nowadays we have, this is kind of a, well, depends of course, concrete, steel, timber, all different story, but roughly so, could get order of magnitude. And then if you take multiplication and you get this number. So it just shows the magnitude. And this is from the source is actually missing, so this is British Institute of Structural Engineers. It should be there, the source of. But these are globally kind of realistic average numbers.
The key thing is to do this without the bridge falling down, right?
Of course. Well, yes, and that's the point of the talk. So the example is this one. Maybe this is not one. Of course, one should not play down things that one is presenting. But I mean, we are talking about secondary structures here. Of course, in some cases, the volume can be quite large, but we are not talking about concrete here. So we are talking about this certain very extremely light, extremely thin profiles, would be less than 1 millimeter extreme. So secondary like type of things shown here, but they can also are used as a secondary structures in a larger construction project. So they are being used and they bear some bare loads, and certain cases can be used as primary structures as well. But why this is good for this this machine learning is that now, because here these are very thin, so they are very highly susceptible to buckling and geometrically nonlinear effects, and that's kind of maybe area where these machine learning tools could be especially useful. So it's quite simple in a sense. So we are analyzing this type of a C profile. These lips here don't play a significant role. I mean, they are a little bit exaggerated here. But then there is this stiffener here. So the parameters are basically the global overall dimensions. Of course, these are something that are dictated from the application also partially, and then there's the thickness and this angle and the idea here is now what has been done is that, okay, this is now just finite element analysis is being applied to generate a data set based on 140 configurations representing realistic profiles. And then, and the consideration is now pure bending. There are, of course, other deformation modes as well that can be critical, but this is now the situation. So these configurations are then picked using the CCD rule to pick from the data a parametric space, the parametric ranges, which are constrained by then design criteria or design regulations, limited these configurations, and then the bending capacity is calculated based on that nonlinear finite element simulation, which is validated again with a restricted set of experimental results. So, okay, now the underlying assumption is that, okay, these are validated and verified numerical simulations that are used to generate now this data set of bending capacities.
I missed something, sorry.
Yes.
You say 140 high fidelity nonlinear FE simulations.
Yes.
Which nonlinearity are we talking about here?
We are talking about both geometric and material nonlinearity, but these are calculated using shell elements.
So basically large deformation. Okay. So
yes, large deformations, abacus calculation.
And this is like a hyperelastic material, not necessarily.
No, it's
like
elastoplastic. So there is but like I said, this is not extremely critical from that material point of view. So this is mainly geometric. Yes.
No. Please, you're not. But I have another question.
Yes.
Okay. So the experimental data is not part of your data set.
No, experimental data is from the literature.
Yeah. Okay.
So this is yes, but it's and there are also other profiles, but that's well, we a little bit discussed this, but this is just that in certain communities, and when you go to this more design, I mean, they are really after that. I mean, if this validation is kind of missing, then it's no go. So there somehow has to be addressed, even though this completely. Yeah, but this is a long discussion otherwise. But yes, the verification and like mesh convergence has been then analyzed separately. But there is just that. Yes. Did you have another?
I want to know if there is some validation of these 140 high fidelity non-linear simulation, right?
No, only part of them. Very
Only part
limited.
of them.
Only limited ones are.
But are you not talking about validation right now? Because you have to test there.
It's an iterative procedure, so.
The validation is not the main thing, but it kind of, the test reflects here that, yeah, it has also been validated against experimental results and the literature for certain configurations. And then we trust that, okay, it works for other configurations as well. But yes, this validation is not the
Yeah,
point.
so it's like a pre-validation, right?
Yes,
Because you need to have this early sort of validation to get.
Yes. But still, I mean, this analysis, I mean, of course, this is not very, well, but it's quite demanding, this, even though they are simple structure, but for several cross sections to do the geometrically nonlinear analysis, I mean, there are a lot of finite element analysis there. So now, of course, the point is that, okay, we build now this, am I missing the, yeah, well, here is the, so we are building this machine learning / regression model to predict the moment for any configuration based on this generated data set. And well, there is some, not maybe shown here, but also this statistical analysis has been done related to now that these various parameters there that are there, is there a correlation between them, and there is some correlation between these overall dimensions, partly arising from these constraints, we believe, but mostly they are not correlated. So it seems that it really, the dominant nonlinearity arises from the actual structural response. In the paper, there is this comparison. I mean, there's lots and lots of comparisons about different models now, but the classes are well, single or simple models. So basically starting from linear regression, I mean, least squares, pure such, and other regression-based predictions. And then there are the so-called ensemble models, random forests, and different learning algorithms of machine learning. And then as a third categories are then these kind of models of models that are like a combination of those three other models.
Let me interrupt just to be clear. Here, the inputs that you're considering are the things that you mentioned, these with thickness and whatever, and the output is the ultimate stress, right?
Yes, ultimate bending moment.
Bending
so
moment,
like a stress resultant.
But the inputs are these B and theta.
Exactly. These parameters, purely geometric parameters, are inputs, and we try to construct a function M ultimate as a function of these ones. And these prediction errors, error variability, and robustness across the calibration domain were considered as comparison domain. And now, I mean, this bias, so we now take this so-called high fidelity FEM, so that's our reality. In finite elements, we trust at this point. But the observations are such that for these simple regression models, there is a very large variability in terms of those indicators, those root mean squares, and biases. These ensemble models are better, and then by stacking them together, there is possible to have so-called best generalization in terms of these average errors. But as the data shows that even if there's like a low average error, there can still be large deviations in the capacity, like outliers. And also what we observe is that these surrogate models, or they are not conservative. Well, of course, there's no reason to believe that they would be conservative, but in the structural engineering, it's very conservative field. So usually, I mean, this is also a little bit game stopper, that if you show something that is not conservative, so for many designers that are responsible, safety critical or non-conservative always said no.
What means conservative?
Means that we predict larger capacity than it is. So
on the right side of the
not
prediction.
conservative, yes, because now we are predicting this M ultimate is the capacity. So if we overestimate it, then we are not conservative. But like still, it's quite this represent the data, but in many areas of this domain of calibration or domain of validation, like it is quite okay. So these biggest outliers are typically near the boundaries. So especially for thick, low-height sections, there is overestimation. But then and now here it is chosen this meta model to calculate the capacity. So if we now compare it on average in a certain set to this PEM, so this is the kind of average overestimation or level of non-conservativity there, but there is also deviation and so on. So now actually I did not mention this, but this DSM refers to the direct stiffness method that is used in American standards. So for instance, here, this is in the design standard, this is of course makes very happy. Yes, we are always on the same side. But even there are a few cases where it is non-conservative, but not very much. So, that's the interpretation. So at this point, like I said, this is mostly the capacity prediction using this type of model. There is also a follow-up work coming where this model, because now or this machine learning model would be actually used then to kind of in the design that, okay, let's say you have P and H coming from somewhere, so what kind of stiffeners I should put there. So of course, usually the old way there are these design curves, and then you pick a point and say, okay, this is the thickness I need to take, and this is something we are trying to construct and to some extent have been successful, but we were also looking at the symbolic regression because that we would get a nice closed, expression. Okay, here is an expression we can use, but the expression's very long. It's still not good so basically you need a computer to evaluate it. So trying to, because the traditional engineering is in a very conservative based on given design curves, then of course that if you go to this high fidelity analysis is too much in many cases, but it seems not so easy to generate something in between, but this follow-up aims to that. But and it also considers the European standard, which by the way turns out to be very conservative. So that's of course an observation of its own. So because this is the stiffness method, then the European standard uses so-called effective width method, which is yet another method based on beam theories, but it does not account these stiffeners basically at all realistically, so it leads to very conservative values. So of course that is also as such critical in terms of the sustainability considerations. Yes.
I'm guessing the idea to do this is to do it, I guess, quickly, right?
Yes.
Because otherwise, we will do a finite element simulation, right?
Yes, exactly. That's
and
the
then we
idea.
get the correct answer, right?
Yes.
If you're willing to wait, you just do a finite element simulation,
Yes.
right? Okay. So I'm guessing this is going to be very quick. Are the other European standards also very quick to compute?
I mean,
these little, I don't know, these little formulas, DSM and the
so yes, if one knows what one is doing, it's quick, and from in terms of floating point operations, they are very restricted.
Okay.
So but this is another fundamental challenge. Of course, we are kind of that. We are going maybe one step too far because the first. That okay, maybe we should just use even finite element analysis to make a little bit more realistic predictions. But like I said, the problem there is that even though we know that it's not so big of a deal, but still, I mean, in a field practice, I mean, it's not. And again, if you want to do structural optimization, I mean, you need to do a lot of them, and some kind of optimization algorithm needs to be there anyway. But it is where we are with this one right now concerning this AI assistance. I will go a little bit accelerate, but this was actually one of the main things, and also it was in the title. But I will briefly talk about this reliability under environmental uncertainty, because now we kind of, okay, we saw that there is uncertainty, and now here we try to really discuss it. So these extreme snow loads have caused actually in Finland multiple large span roof failures in recent years, winters. And these mechanisms, I mean, there is not a single reason that is to be identified, but often they are linked to load uncertainty, accumulation effects, and some operational decisions that are being made. So, well, needless to say that, okay, this nominal design, which we were also discussing, I mean, that's not enough, but we need to address this uncertainty in these actions and in the snow loads. So now a little bit more mathematically, a structural component can be characterized as a group of random variables referring to its properties and the situation, and then we can define this limit state function, which is the resistance minus the effect of an action. And so if this limit state function is positive, we are safe. So the resistance is larger than the effect. If it's negative, we are unsafe, and at the so-called ultimate limit state, we are at zero. They are equal to each other, and that's kind of the optimal situation that one would aim at, so that all capabilities of the structure are being utilized to resist the effect of an action. So in context of permanent load and one variable load, here meaning now snow, which is quite often the dominant load, and sometimes it is even the single only dominant load in certain situations. In typically, so there is included certain modeling uncertainty for both the load and the resistance, so that we have this kind of a limit state functions, the resistance minus the load multiplied by these uncertainties. So we have, well, here also 5 component random variable. So the self-weight, the snow load, the resistance, and those uncertainties. And then this failure probability is being defined based on the joint probability density of that random variable. And of course, in general, it is a challenge to evaluate such, or even to determine the joint probability density, or not to compute that probability. But now again, if we go to the standard, so this is what is in Europe required for this. So what is the allowed probability failure? So first of all, the standard consideration is a 50 years time period. And this is defined in terms of the so-called reliability index beta, which is defined in terms of the normal distribution. And it is explicitly said in the standard that target reliability for a 50-year period in Europe is set to 3.8, which means that almost every 10,000th construction may exceed the 100% utilization rate. So it doesn't mean that the structure will collapse, but that, okay, it's all being overutilized. It's on the red zone. And now that's how it should be. Well, how is it being designed then in Finland? So first of all, there is the characteristic snow loads, which depends on the area. Oulu is there. So no, here, there. There's also some interpolation involved if the construction is not uniquely defined. So then you interpolate from the lines. And this is here on top is the highest, but also here near Oulu there is quite high. Of course, there is not so much large span construction in this area, but for instance, here there is, and of course it's quite high also south here when you go away from the coast. So this is the nominal snow load, so kilonewtons per square meter on ground for a 50-year period. And then the design rule is this one. So here we have partial safety factors for calculating the effect. So to take the uncertainty in the load into account, so that this self-weight is multiplied by 1.15 and then the live load by 1.5 to take into account that. So this is the method of partial safety factors, so that.
So what was GK is which?
GK,
Yeah,
that's the self-weight.
Self-weight and QK?
That's the snow load.
The snow load and the self-weight.
Yeah. So here, I mean, of course, have to be in the same unit, but this is how you combine them. Or then there is this kind of a special rule that it's the less favorable from these two. So just the self-weight multiplied then by 1.35. But actually, this is the little bit critical thing here, that why is it being reduced here? Because this is kind of the first, of course, that it has to hold its own weight. But then if you add live loads, suddenly this drops this safety factor. Why?
What's the difference in magnitude between G and Q?
Okay, of course that's the critical thing and not easy to explain. This is now on a very general level. And actually, here is just something how to calculate. So there's this first order reliability method so that you transfer that approximate that probability distribution first order and approximate by normal distribution and calculate the integral, or then more brute force way. But it is just shown here that, okay, this first order method and Monte Carlo here, they are quite close to each other when this was the 3.A was the target reliability. So if we are in this area at least. But I don't know, not sure if I'm able to fully answer your question, but now what we have done, so we take a textbook truss. So this is a critical structure in a sense, so large span truss would be tens of meters even, and then put the load. And now, because here is the ratio or the portion of the live load, in this case snow load, of the total load. So Q over G plus Q. And what we observe, so here is the present combination that is being used. And what are these points? So those points are now rational designs. So they are basically rational cross-sections, rational steel quantities for these elements. Under this, so there's the self-weight considered and that load. So each of these points represents something that with these partial safety factors could be constructed somewhere in Finland. And what we observe, first of all, which is of course quite natural, that as this share of the snow load of the total load. So if there's a lot of snow load as compared to the self-weight of the structure, the reliability decreases. And it decreases in many cases below of this target reliability. Here are earlier factors that have been used in Finland, which seem to be better reliability. Here is sort of the standard where this reduction from 1.35 to 1.15 is not being made. So, but even with that choice, there are some rational designs that again give a little bit lower reliability. And it seems that, well, we are not alone in sense that there's also a study, fairly recent study in structural reliability, where they propose, I mean, extremely high safety factor for snow, 2.35. And that, I mean, that would be already like 11, that's overly conservative. And of course, here again, the question is that how to do this calibration. So now the way to calibrate is, okay, we are just like trying different combinations. And of course, in the underlying, I'm not showing, we have also the probability distributions are being assumed. For instance, for the snow, it's this so-called Kumbel distribution, but for the others, self-weight and the resistance, I mean, it's normal distribution to begin with. So there is some sensitivity to the assumed distribution, but actually not that much. Yes.
How does this translate to material saved or cost saving? Because sometimes like
Yes.
just putting a little bit more like it makes it well, to have that you would require a ridiculous amount of material, so it's not linear basically.
Exactly, this is a very non-linear problem, and that's why we struggled because first I did this myself only. And I just have this single graphs, very generic that, but I think that the general idea became clear there. But of course, every time you change the coefficients, also these rational designs change. And this is exactly what is now being taken into account, that all these designs are based always on these coefficients, because then what you can get, and there are also different steel grades, but that's the impact is huge. I mean, this change then, and that's not really addressed here, but of course, if you change one of these coefficients, it will affect all designs and what kind of profiles and how much steel you need and how much carbon you have. So, and so on. But clearly there is indication that this is not okay, and I have said it out loud, that this should be changed. This is not okay.
So you want it to be more conservative or less?
I mean, this should be, and we are still kind of formulating that. Well, of course, even this is kind of the standard choice would be better. But like I said, if you increase this, that will influence, there will be heavier materials, heavier constructions.
Yeah.
But you want to, of course, to avoid all the dots below the red line. Right?
Yes. Well, yeah. Well, that's also that. Well, at least there's too many dots below the red line here. Way too many. But of course, then the question is that where are these? So it depends on the map. So these are typically, you have to be somewhere where there is high snow load, where this T is high. But there are quite many points, on the other hand, in this area. But there is also more of these studies, more of the results coming up, that how the material influences, but the basic result is there. I'm running out of time, so, but to complete, I will just, and this is partially known, but the finite element approach is still the same. We are working on this, something in between the strict mathematical model, which is rigorously defined in terms of differential geometry, and purely approximative model based on isoparametric principles, so that we utilize the normals to calculate the curvatures inside the element to get a slightly better geometry approximation, and then transforming the degrees of freedom accordingly to this so-called assumed curvilinear coordinates that are these local by local. But so the curvature is there, but this is something that now when we talk about the triangular element, and if we take now the kind of from the literature, well, this is still from the 2017, but seems to be the state-of-the-art triangular shell element, linear element. Well, we get similar performance for coarse mesh, few percent better, but that's also work ongoing. So more traditional computational finite elements. That's also, I started a little bit late and finished a little bit late.
There are plenty of questions in the middle, so
Oh,
thank you.
there are more.
your last slide, you generated a new element, or you somehow changed the shell element?
This is, well, it is a new element in a sense that it is based on this shell theory where this curvature is being explicitly calculated from those nodal normals. And then these strain reductions are being imposed to deal with membrane and shear blocking, which are also needed here, but the membrane blocking is not being treated explicitly because there is no curvature involved.
And the advantage of your element is that the curves are the same.
Well, now I'm saying that it is at least as good as this one. And by the way, they also use cubics for so they use higher order there. Even though it's linear, they need higher order quadrature also, which is not very explicitly said, but we really work with this linear degrees of freedom. There is the shear stabilization and a stabilization parameter is being involved, but it is what it is.
So it's not conforming.
It's non-conforming, but it's more conforming.
Okay.
That was the where I started from. It's not non-conforming, but it's more conforming. And of course, this is the question: to conforming to what? But if we have an idealized shell model where the geometry is based on differential geometry and parametric mapping and not approximated by finite elements. And these nonlinear problems are coming.
Yes, thank you for the talk. I'm wondering where this magic 140 samples number shows up.
Yeah, good question.
Is, for example, like Monte Carlo sampling of the parameters, or like they chosen according to a certain methodology?
You need 140 high fidelity.
The high fidelity simulations for training the reduced model. Yes.
Yes, it's of course somewhat arbitrary choice, but based on kind of the parametric limitations that there are from in the standards to those, and what is the design.
And do you oversample near the boundaries, because sometimes you need to do that near the boundaries of the parameter space? I mean,
Well, it is this. It should be fairly standard, the CCD method to sample this.
okay, so probably that's the answer.
Yes. So in that sense, it's not arbitrary. So the samples are picked using this, but that how many calculations have been made, that's of course.
Sometimes when you do machine learning and AI, sometimes you have to be a little careful closer to the boundaries.
Oh,
of
yes.
the parameters.
And is, for example, convergence of the high fidelity models also a problem when sampling? You try a parameter that's too bad, you don't get convergence, or maybe the nonlinearities of the high fidelity model are not so terrible.
Yeah, yes, but there is, like I said, some engineering judgment is also involved. But that's where we, like you said, near the boundaries, we observe. But I mean, we still believe that, of course, the finite elements, like said, can it be completely trusted? It's a good question. And like said, the many engineers, I mean, they don't trust that either, that it's only this clear stiff method, different method, or the effective weak method is the only other.
I see, thank you.
Yes, was very good.
Any other questions? Okay, thank you. One last question.